Thanks very much. Yeah, I'll try to introduce those climate tipping points, and then I want to talk a little bit about how there are general early warning signals of tipping points in complex systems, and we can see those early warning signals before tipping points in the climate system. And maybe you've heard a tiny bit about that topic from other speakers. We'll see. Okay, let me just share the screen and we can get started. So, just going to go backwards a bit. So yes, climate tipping points. But to start with, I'm going to just show this movie of a system with two alternative stable states, the two valleys, and I'm forcing this system towards a tipping point. I'm forcing it fairly slowly, and it's also subjected to some variability, some noise that's pushing the ball around. But as we can see, the state the system started in is losing stability, and at some point, a small nudge there is going to be enough to tip the system from one state or attractor into another. Before that tipping point, if you're watching closely, you can see some general behavior. The ball is going to roll around slower in the valley as it gets shallower before you hit the tipping point. And that really is the general early warning signal that I'm going to come back to later. The general early warning signal that a tipping point is approaching. Now, I'm just going to let it happen once more. There you go. Now, there are a whole bunch of complex systems that sometimes can exhibit tipping points with that kind of phenomenology. So here I've arranged a bunch of different bits of the Earth system in terms of different time scales on the x-axis and space scales on the y-axis, and I'm color coding them a bit, but these are all systems which we have reasonable scientific evidence and understanding to suggest that they can sometimes pass a tipping point between alternative states or attractors. I've just color coded them. So blue is aquatic bits of the Earth system. Green is terrestrial ecosystems and biosphere. Gray is stuff of the land-water interface. The gold color is key bits of the climate or the Earth system on large scales, and the red is social system tipping points. This stretches right back to things deep in Earth history, but I'm going to concentrate on a load of stuff in yellow or gold on fairly intermediate to long time scales on large spatial scales. But I'm also going to touch a little bit on the risks that tipping points in the climate system might risk some tipping points in societies. The one we really want to avoid is in red in the middle there, civilization collapse. I'm not going to talk about positive tipping points in society, but you're welcome to ask me some questions about that afterwards, because I believe we see evidence of those as well. But my main focus for about 20 years now has been on trying to identify what are the large-scale parts of the Earth's climate system that could pass the tipping point due to human activities this century, shall we say. And actually, there's something on the map here, the Antarctic ozone hole, that passed the tipping point in my lifetime later on last century and is sort of slowly repairing. Everything else on the map here are things that back in 2008 we thought could exhibit a tipping point and could be pushed past it this century. We'll see in a minute that we've just updated this map, but even back then there were a host of different systems. Some we were more confident about than others, so ones we were less confident about we had a question mark on back then. So what I wanted to say first was, well, how would we have evidence to suggest that these were bits of the climate system that could have a tipping point? Well, one source of evidence is what's gone on in Earth's past. So this is a record from an ice core drilled in the Greenland ice sheet of about the last 80,000 years. So most of this is the last ice age, and then the last 10,000 years is what we call the Holocene interglacial period. But what this is showing is a proxy for temperature at the ice core site in Greenland. And you see it changes abruptly a number of times. There are 20 numbered abrupt warming events that later on are followed by abrupt cooling events. These correspond to warmings of around 8 degrees centigrade at the location of the ice core, and those warmings happen within a couple of decades where they can be resolved precisely. So this is very abrupt climate change, and it's not localized to Greenland. It has ramifications around the northern hemisphere, the tropics, arguably throughout the world. And these abrupt warming events, they have a name, Danskard-Oshkosh events, after their discoverers. So they serve to illustrate clearly that Earth's climate is not always stable, and it can do pretty abrupt and striking changes, including coming out of the last ice age. So if we just zoom into that a bit, we zoom into this interval here, we see several of these DO, Danskard-Oshkosh events. And then, well, the one that's labeled number 1 up here, that's referred to by paleoclimate people as the Bolling-Allerod warming onset. It's a very abrupt climate change. Then over here, where I'm speaking from in Europe, we get this signal. There's a subsequent cooling. We call this the Younger Dryas colder period. But then there's another abrupt warming to finally exit the last ice age. And it looks like things calm down, as seen in Greenland. But actually around the tropics, including in India, there's some rather abrupt changes in the water cycle and the monsoon systems that occur every now and again during the Holocene. And those have been linked to the rise and fall of past civilizations in different parts of the world. So clearly we have some hint that there are instabilities in the Earth's climate, and we also know a little bit about where they come from. So we know that the great overturning circulation of the Atlantic Ocean is implicated in all of these abrupt shifts, that there are tipping points between different states of the Atlantic Ocean's circulation that have played some role in this, but they seem to be coupled fundamentally to the atmosphere and also to the monsoons, as we'll see. The other source of evidence we might use to look for where could climate tipping points happen is the elaborate climate models we have and that are used to make future projections of climate change. And this slide is just summarizing that in those models and those model projections, actually one can find quite a lot of abrupt changes going on in different models in different parts of the world. So on the left, it just shows at what global temperature level at or above pre-industrial do you get these abrupt shifts in different models, and do they happen in the sea ice in blue, or circulation in pale blue, or vegetation in green, or land ice in gray? And then over on the right, we just see some of the places in the model worlds where abrupt changes happen. So that includes clearly lots of stuff going on, for example, in Antarctic sea ice cover, but also parts of the circulation of the Atlantic Ocean, the regions where deep waters form in the Atlantic Ocean here on the left and the right of Greenland. These often see model abrupt shifts there, but also some other possibilities crop up in the models, including dieback of the Amazon rainforest in some of the models, which I'll come back to as an example. You'll also notice that in the model worlds, quite a lot of abrupt changes go on at low levels of global warming above pre-industrial, between 1 and 2 degrees C, for example. A level a danger zone we're already in, if you like. And then a key source of evidence that's accumulated in the last decade or so is just the direct evidence from bits of the planet that they're changing, accelerating change in the wrong direction and showing key signs of instability. So obviously in all this, we need to use our understanding of complex systems and especially the feedbacks within bits of the climate system. And for a tipping point to occur, the key criterion is that there's a reinforcing feedback within that system that can get so strong that it can become self-propelling. So you take the forcing away, but change would just self-propelling the system. And all of these things dotted in red are systems where we've got reasonable evidence for those potentially really strong self-propelling reinforcing feedbacks. And we've also got evidence from observations that there's some acceleration going on in terms of the change within the system. So I won't go through all of them, but there's compelling evidence for accelerating loss of the Greenland ice sheet and potential having already passed a tipping point in the West Antarctic ice sheet. If you're curious, between them, those two ice sheets hold enough water to raise the global sea level by about 10 meters. So they can't melt that quickly, luckily. It takes multiple centuries. But we could be very close or even past tipping points that commit the world in the long run to 10 meters of sea level rise. You see that little note on the evidence here that there's unprecedented droughts in the Amazon rainforest. I'll come back to that example later. But also there's been this marked slowdown in the Atlantic Ocean's overturning circulation that drags heat from the southern hemisphere to the northern hemisphere at the surface, and then deep waters form either side of Greenland. That whole system has slowed down markedly in the last 50 years or so, and I'll come back to that example as well. So it's these different sources of evidence, like what happened in Earth's past, what do our models predict, and what's going on directly in the observations, that cause us, as we learn more, to adjust our risk assessment of where the climate tipping points could be. So basically, the Intergovernmental Panel on Climate Change includes this sometimes, at least in its general assessment of climate change. But back 20 years ago, the general thinking among climate scientists was that it would take 4 or 5 degrees centigrade of global warming to put tipping points at serious risk. But all this evidence I've just been summarizing has unfortunately led to a rather different conclusion. And over time, we've been kind of increasing our risk assessment. And even the Intergovernmental Panel on Climate Change by 2018 and 2019 was suggesting that there was a risk of climate tipping points already where we are at about 1.1 or 1.2 degrees C of global warming. And by the time you got to 2 degrees C of global warming, well, that risk was becoming significant. So just recently, as you heard, we published a paper in Science where we tried to update the list and the maps of the climate tipping elements, as I call them, and also reassess all the best evidence we had for what their temperature thresholds lie, if you like. So at what level of global warming could they be tipped? So we decided to split what I call the tipping elements into global core ones on this map, and then some ones we're going to come to, which I call regional impact ones. So here, the global core tipping elements are things that if you tip them, it changes, you notice it in a global sense, it changes the whole kind of mode of operation of the Earth system. So this is things which tip on a really large spatial scale and or have a global impact in terms of their feedback to global mean surface temperature, that's GMST down there, so that they would add at least 0.1 degrees C to global warming. And that's the case, for example, for abrupt shifts in the boreal permafrost. So you see some things that were on the maps before, but we also see the addition of the possibility that the evidence that there is tipping points for parts of the East Antarctic ice sheet, as well as maybe the whole East Antarctic ice sheet. And also there's something here, Labrador Sea or subpolar gyre SPG convection, that's coupled to but distinct from this Atlantic overturning circulation. And that's a kind of a new tipping element on the map, and one that could be at risk at low levels of warming and has big impacts for for me and everybody else living over in Western Europe if it was to tip. Now, the other category, the regional impact climate tipping elements, these are things where we're not sure that when you tip them, it sort of has obviously global impacts on the whole state of the Earth system, but there's things where we know that a lot of humans depend on these systems that can tip, and or they have great value in themselves just as a unique feature of the Earth system. So we do have at least one monsoon system on this list, the Sahel and the West African monsoon. You'll notice that I'm not, at the moment, I don't think there's enough evidence to keep the Indian summer monsoon on the list, but our evidence and our understanding is changing all the time. And I'll say a few more words about that in a minute, about whether there could be a tipping point for the Indian summer monsoon, or indeed the East Asian monsoon or other monsoon systems. But first, a little bit of the summary we made about at what global warming level would these different tipping elements be at risk of tipping. So this is a lot of information in this slide, but if we just concentrate over here on the burning embers, as I call them, we've got a temperature scale here. We can kind of ignore the colder temperatures. 0 is the pre-industrial level. We're at the current warming level, 1.1, 1.2 degrees C here. And this is global warming going upwards on the y-axis. Then we've listed all the different systems you just saw on those maps. But the ones in bold were the ones that fit the first map of global core tipping elements, and the ones in normal font are the regional impact tipping elements. And then you see like this burning ember, which represents the range of temperature estimates at which the tipping point is for each of these systems, coming from different models or past evidence from the paleo record. So when it gets to dark red at the top, that's where we're thinking, well, it's quite likely that the tipping point will be passed. When the colors start to go yellow at the bottom, it's like, well, maybe one model suggests there's a tipping point. In the case of the Greenland ice sheet, one model gives the tipping point already passed because it was at 0.8 degrees C of global warming. And the dotted line is our best estimate of where the tipping point might be based on looking across different models and other evidence for that. And if our estimates are right, we think that at around 1.5 degrees centigrade of global warming, all 4 of these systems here, a tipping point becomes, well, we call it likely, but you hit that dotted line, it becomes a definite possibility. It was possible already, but it becomes more likely. And then there's some other systems for which the tipping point could be pretty close and below 2 degrees centigrade of global warming, including that Labrador Sea thing I mentioned a minute ago. But note that those 2 big ice sheets, Greenland and West Antarctica, and their 10 meters of sea level, they could be a couple of the nearest tipping points. We definitely think low latitude coral reefs are at risk of widespread tipping at 1.5 degrees C of warming. And so is a large chunk of the permafrost, the frozen soils of the high northern latitudes. And so they could thaw abruptly on a large scale at just above the present level of warming, and that would add significantly to the global warming in that case. You could ask me more about the other systems later if you want. All the information on the right is just showing different IPCC climate projections into the future by a kind of color scale from the blue low levels of warming to the red high levels of warming. And then this stuff down at the bottom is just, well, how many tipping points do you cross and when on the different red, orange, yellow, green, blue trajectories? And I guess the message is fairly intuitive, which is if we could limit global warming to just above 1.5 degrees C, the blue trajectory, I'm afraid we'd still risk maybe those first 4 tipping points, but we could avoid the rest. Whereas if we just carry on the trajectory we're kind of on, which would be something perhaps like the yellow or the orange, we're going to hit more tipping points and we're going to hit them sooner. So that's considering those tipping points as if they didn't interact, as if they were just functioned in isolation. But we also have some evidence that perhaps unsurprisingly, they interact in a causal sense. The whole Earth system is coupled together. I drew this little sketch up a few years ago to illustrate one of the chains of causal interactions. So we know that the Arctic sea ice is being lost at an accelerating rate, and that this is responsible for what we call Arctic amplification of global warming. Basically, you replace a really white reflective surface with a really dark absorbing blue ocean surface that absorbs loads more sunlight, heats the Arctic up way more, that melts more ice, and so on. That's why the Arctic's warming 2 or 3 times as fast as the global average. It's contributing to the thawing of the permafrost on the nearby land by warming it up, but it's also contributing to this accelerating melt of the Greenland ice sheet. And when the Arctic warms, you get more precipitation up there. So you've got more fresh water coming out of the sky as snow or rain, and you've got more fresh water pouring off the Greenland ice sheet as meltwater. And both of those sources of fresh water head into the North Atlantic Ocean, and they make it less salty, therefore less dense, the surface waters, and therefore less prone to sinking from the top of the ocean to the bottom, because it's this extraordinary process of deep convection where normal conditions are that surface waters either side of Greenland get cold and salty enough and therefore dense enough to convect from the top of the ocean to the very bottom. But that process is getting interfered with by this extra fresh water that's freshening those surface waters and making them less dense. And that's why we think the Atlantic overturning circulation is slowing down. And that overturning circulation, it's dragging heat from the southern hemisphere to the northern hemisphere. It's setting the position of what's called the intertropical convergence zone, but in common language, the band of rainfall all the way around the tropics. It tends to shift that to the north, but as it weakens, that gets shifted further south. So that affects the monsoons in the tropics. And as it weakens, it leaves heat behind, if you like, in the Southern Ocean, which is a big risk for the ice sheets there, because water holds a lot more heat, it's got a lot more heat capacity than the air. So it's the warming of the ocean that touches the ice sheets that's the big risk factor there down in the Antarctica. So what we're saying is you've got these tipping points and tipping elements that couple together in a way where tipping one thing makes tipping another more likely. And then the worst case scenario, you could think of it like when you line up the dominoes, when you tip over one domino, it tips over another, and it tips over another. So that was our kind of sobering assessment of where we are with the climate tipping points. And this is just to show you something from going back into Earth's recent history. I'm afraid time is going in a crazy direction now from the right to the left, but that's what geologists do. They put time in a counterintuitive direction. I showed you before this record of all these abrupt climate changes from a Greenland ice core. That's just that same record we saw earlier in blue, but the time's been switched around. The other interesting information on this plot is some proxies for the strength of the monsoon in the Amazon in red here, and the strength of the monsoon in India in green here. Just to add to the excitement, monsoon getting stronger is upwards for the green record, but downwards for the red record. But if we just concentrate on India, as that's where you are, when there is abrupt warming in the northern hemisphere and recorded in Greenland, there is also abrupt strengthening of the monsoon in India. And when there's abrupt cooling in Greenland and the northern hemisphere, there's abrupt weakening of the monsoon in India. And that happens every time, if you like, repeatedly. So you see that even coming out of the Ice Age, monsoons suddenly get stronger, suddenly gets weaker, suddenly gets stronger again. It kind of makes sense. We can talk about the mechanisms, but when you have an abrupt warming of the northern hemisphere landmass, that's the thing that contributes to switching on the monsoon circulation, the fact that the land warms faster than the ocean in the summer, and then that sets up the monsoon circulation. So it's kind of intuitive, but what we're seeing here is a strong coupling between the tipping elements, so that when you tip what we think is a tipping of the Atlantic overturning circulation, you get a corresponding tipping point in the Indian monsoon, and probably also the Amazon and the South American monsoon, although it turns out that South America and the Amazon are tipping in the opposite direction to monsoon weakening. So that gives us evidence that these tipping elements can really be coupled, because they coupled like 20 odd times in the past. And then there's been an on-running discussion or debate about whether there could be a fundamental tipping point in the monsoons, be that the Indian summer monsoon or the other monsoon systems. The core idea here would be there definitely is a strong reinforcing feedback built into the monsoon. Basically, when the monsoon circulation gets going, lots of moist air being drawn in out to the land and then tending to rise over land. And when that moist air rises and enters into cooler air at greater altitude, tends to cause the release of latent heat as the water condenses and the monsoonal rains pour out. And that's actually, when you do the calculations, that's a lot of latent heat release that is supporting the monsoon circulation. It's propelling or supporting the upwards convection of the moist air. And then you have the drier air returning at altitude back over the ocean, dropping, and the circulation continues. So the point is, there is this really strong self-propelling or reinforcing feedback built into the seasonal monsoon. The debate is over, is that so strong that you could have tipping points between a monsoon on and a monsoon off kind of state? And some people argue you could, and some people argue you couldn't. I will, well, we can come back to that in question. So that's why I haven't got it on the map, because this is a kind of unresolved issue, I think, but worthy of further research. I'm sure you're aware of this already, but there is direct observational evidence that there's been disruption of the Indian summer monsoon over recent decades. And that is principally because nothing to do with, not because of global warming, which, if anything, should strengthen the monsoon, but rather because of the haze, because of the so-called atmospheric brown cloud of pollution over the Indian subcontinent. That's a mixture of sulfate aerosols from coal burning and black carbon soot aerosols from wood and biomass burning and stoves and everything else. Basically, you put a big cloud of this haze in the atmosphere, and you're going to absorb more of the sunlight in the atmosphere and scatter more of it in the atmosphere, and less of it is going to reach the ground. So that's crucial, because it's the sunlight of summer hitting the ground and warming the surface that's key to switching on the monsoon circulation. So it kind of makes intuitive sense that that pollution has been weakening the monsoon, and it's been also, in so doing, harming the rice harvest, at least over the latter part of the 20th century. Arguably, things are looking a bit different now, especially with this year's tragic floods in Pakistan. We might be seeing what I described 15 years ago as a kind of tug of war between the possible cooling forcing from this pollution and the global warming, which is tending to strengthen the monsoon. So you've got one kind of human effect, the pollution that's tending to weaken the monsoon. You've got this other human effect, the global warming, that's tending to strengthen the monsoon. The two things are sort of tugging against each other. And surprise, surprise, the end result might now be a more volatile and unpredictable monsoon. But you're the experts, you're living there, we can discuss that. I wanted to just move on a bit and note that while I've told you a little bit about how there have been this abrupt climate changes in the past, of course there were people living on the planet when the climate changed abruptly in the past, and there were lots of ecosystems, and we're beginning to learn how past abrupt climate changes are measurably connected to abrupt shifts in ecosystems in the past, and sometimes abrupt shifts in societies in the past. So this little diagram is related to this abrupt warming in Europe and the Northern Hemisphere that happened about 14,500 years ago. But there's clear evidence there that the kind of core climate tipping point triggered a load of tipping points in ecosystems and a load of tipping points in societies that started having to migrate and move around. And that would beg the question of, well, what kind of impacts could future climate tipping points have on societies? And there hasn't been much work on that, strangely. I've tried to do a little bit of work on it, and this is just one example. We took a climate model and we made it have a tipping point. So we forced a tipping point in the Atlantic Ocean's overturning circulation, which includes kind of disrupting or deflecting what over here in Britain we call the Gulf Stream, but this red-orange flow of warm water at the surface. So suddenly, if you have that tipping point, well, it probably tends to cool the UK or counteract the global warming, but most profoundly, it tends to dry the United Kingdom, because this is our big source of storms and moisture. Basically, the atmospheric storm track kind of follows the Gulf Stream direction. So without going through all the details on the right, basically what we showed, we could couple our climate model output to a quite well-grounded model of agricultural farmer choices and land use in the UK. So in the UK, basically only part of the UK is it possible to do arable farming, so grow crops like wheat, and that's what's but that's more profitable than raising cows or pigs or chickens or livestock. So where you can do it, you do arable farming, and that's the brown areas of the UK. And where you can't, you may raise livestock, and that's the green areas of the UK. If you have this tipping point, if we just look at the map F, then, well, the UK dries out so much that it eliminates arable farming, basically. So we'd have major food security issues or dependency on other nations if that happened. But we'd have bigger problems because it'd be so dry in the southeast of the UK, where so many people live, including in London, that there'd be major shortage of water in the summers and so on and so forth. And we tried to calculate, could you like irrigate to recover the situation? So we did a sort of experiment where we imagined, irrigating to recover the situation and be able to grow wheat again and so on. But then we calculated how much water would you need, and we found it was far in excess of the water available from rainfall in the winter. So we concluded you'd have a major adaptation challenge in the UK if you had this tipping point. You'd have to have enormous pipelines piping water from where it would still rain on the west side of the country down to the southeast where a lot of the people are. Okay, so that's the bad news on climate tipping points. And if you're following me, you're probably thinking, could we get a better warning of these bad things happening? So this is my little metaphor for the idea that maybe we're somewhere over here. We're in a boat, hopefully with some friends and hopefully with some paddles, sort of like an open canoe. But we're floating downstream and we're thinking there's something dangerous and probably really bad ahead, probably because we can hear a loud rumbling noise, but we're not quite sure what this bad outcome is or how close it is. We just know as the rumbling noise gets louder that we're probably heading towards it. Now, in this metaphor of sort of floating in a canoe towards a waterfall, there's going to be some point at which the game is up. You're going to have to start paddling hard in the opposite direction before you reach a certain point where your fate is going to be sealed. So we really want to know how close we are to that point of no return. So ideally, we want some early warning signals before we get to a bad tipping point. And as I described earlier with the little movie, there are pretty general early warning signals before a tipping point in any complex system. And one of them is just that the system recovers more slowly from the little shocks it's getting all the time before it tips. So the ball rolls around slower, which is another way of saying the damping feedbacks that were keeping the system in the original stable state get weaker. And before a tipping point, we can pick that signal up. So it's also true that the ball will move a bit further for a given nudge before the tipping point. So we would expect to see, and we measure it down here in red, that the system is slowing down. So one point in time becomes more like another, and that's what we measure here. It's called lag 1 temporal autocorrelation, calculated on a sliding window, but also variance, how far is the ball moving goes up before the tipping point. So general early warning signals, autocorrelation in time should go up, variance should go up before a tipping point in a predictable way. I'm looking at a clock and I think I'm going to skip over talking about the maths of that. I'm just going to ask you to take it on trust. And I just want to show you that those signals of rising autocorrelation and variance happened before past abrupt climate changes. So here's my, going back to my ice core record, I've trimmed it before the final exit out of the last ice age. But if we just look at this Greenland ice core record, we can kind of see that the fluctuations in the system get larger and they slow down before exiting the last ice age. If I try to detrend the data, that becomes really obvious. You get these long-lived large fluctuations that weren't there before. And for sure, the lag 1 autocorrelation and also the variance go up in this record before the end of the ice age. So if people had the maths and the data back then, they'd have been able to see that the end of the ice age was coming. And in fact, before this Bolling-Allerod warming that we talked about, it was also a clear destabilization signal. There's also been lots of work done in models to show that if you force a model past the tipping point, you can see this early warning signal, rising autocorrelation, rising variance. So this was the original study, 2004, by Herman Held and Thomas Kleinen. They took a kind of simplified ocean circulation climate model. They pushed it past the tipping point and they showed beforehand that there was this reliable increase in the autocorrelation and time of the tiny little fluctuations going on in the system. Lots of other groups have looked at that since, my own included. And we've looked in more complicated models like three-dimensional ocean atmosphere climate models, and we've shown for sure there's these general early warning signals, for example, before a collapse of this Atlantic overturning circulation, and that you can pick those up potentially in the places where we actually monitor the Atlantic overturning circulation at the moment, which is at about 26 degrees north. But when you have a model world, you can play games in it. Like you can ask, well, where is the best early warning signal available? Where would be the best place to monitor? And that's what this slide is about. But to summarize, what it shows is the best place to find an early warning signal at this particular tipping point, the collapse of the Atlantic overturning circulation, is in the high northern latitudes of the Atlantic, or maybe near its southern boundary, because the red areas are here are showing where we've done a statistical significance test of the early warning signals against a null model. And the useful information is you can get an early warning signal. In this case, it's a slowly forced system. You can get it maybe 200 years before a tipping point, which is good news. On the other hand, the bad news is this is a slow system, so you have to monitor it for about 500 years before you can hope to get a statistically significant warning signal. So that teaches us something important. We need to know whether we're looking at slow bits of the climate system, which will constrain our ability to get early warnings, and we may be forcing them too fast for those signals to happen anyway. Whereas if we have a faster bit of the climate system, like a monsoon or vegetation or bits of the atmosphere circulation, then we have a much better chance potentially of getting a detectable early warning. However, my colleague Nicholas Bors has looked at real observations, even over just the last 200 years or 150 years, and has published, what he argues is strong evidence for these coupled increase in autocorrelation and variance, indicating loss of stability of the Atlantic overturning circulation. I want to look at one other system before we finish, and that's the Amazon rainforest. So this is a system where we got good reason to believe that there are alternative stable states. If you took the Amazon rainforest away and a savanna sort of grassland with trees in it grew there instead, that would also be a stable state under the current climate, or at least large areas would be. And that's because there are strong reinforcing feedbacks. The forest maintains its own rainfall by recycling rain to the atmosphere, but the forest also suppresses fires. But if fires get a foot in, they destroy the forest cover. So you've got these two different local and large-scale reinforcing feedbacks that can give rise to alternative states for the Amazon. There's lots of interesting modeling work that shows how if you take out the forest, say here nearer the mouth of the Amazon, you get less rainfall recycling, and then that threatens the forest further from the mouth of the Amazon up against the Andes. And equally, you have climate models where if you take the forest away, it doesn't really grow, and you can see that also that the large changes of dieback in the forest can be committed at quite low levels of warming. So these are lots of reasons to think maybe the Amazon could be vulnerable to a tipping point. So we thought, why don't we just look at in satellite data that monitors the forest, particularly satellite data that monitors the vegetation and its kind of fluctuations in water content, which is a good proxy for fluctuations in the biomass of vegetation. Let's monitor that and see if we can see whether the autocorrelation of the data is going up or down, and that's what this movie is showing. So it's actually showing that through the late 1990s, the system might have been getting more stable, but in this part of the movie, the data is showing that the autocorrelation in time of this vegetation biomass proxy is increasing over large areas of the forest. You get the darker blue colors. So probably there's some component of internal climate variability here that was making the Amazon get more stable in the late 1990s. But over the last 20 years, we got a compelling signal that it's got less stable. And that's an interval in which we have very unprecedented droughts in the Amazon in 2005, 2010, and again in 2015. And we actually pick up the impact of those droughts on a marked loss of stability in this data set. So our conclusion is there's some evidence the Amazon is heading in the wrong direction towards a tipping point. It's definitely got some evidence it's losing stability. And we looked a bit deeper. So this is just a summary of that, showing the overall trend in this early warning indicator over space, and then sort of aggregated into the mean. And where it's red are places where stability has been lost over the last 20 years. Blue might be some regions where it's gained, but the red far outweighs the blue. And then we could break this down and we could show that basically drier places that were drier anyway in the forest were losing stability faster or more, if you like. So they're the darker blue regions here compared to the wetter ones in yellow here. So you get a stronger upward and a more statistically significant upward trend in the loss of stability indicator. And we could also show that stability was being lost faster or more nearer human activities than further away. The analysis gets a bit unstable when you get as far away as you can from human activities in yellow, because you then are only looking at a few disconnected patches of the Amazon. But when you look at the places nearer human activities in the dark blue, there's lots of connected data, and for sure, the closer you are to human activities, the more stability is being lost. But what's really interesting is that signal shows up at quite a distance from human activities, like hundreds of kilometers, begging some interesting questions about what the causal connections are. And finally, my colleague Nicholas Bors has been looking at the South American monsoon and looking to see, is there a sign of loss of stability in the monsoon, because it's strongly coupled to the forest. And the short version of this figure is, yes, he sees the same early warning signals that the South American monsoon may be losing stability. So that's enough from me. My summary then is that we're already running the risk of crossing some climate tipping points. And if we go above 1.5 degrees C of global warming, then some of them are going to become likely. and we're going to have to work out how to adapt to the inevitable. I tried to show you that the tipping elements can interact, so that tipping one increases the risk of tipping another, including, crucially, the potential to tip monsoon systems if we significantly weaken this Atlantic overturning circulation. I've also tried to show you that there are general early warning signals before a tipping point in pretty much any complex system, not just the climate, but that we've been able to find those early warning signals in real data in the real climate system, supporting the point at the start that we really do see several tipping elements in the climate system losing stability and heading towards their tipping points, I'm afraid. So it's a sobering talk, but maybe forewarned with some complexity science is forearmed for some bad changes that might be coming. Thanks for listening.
Thanks, team, for this excellent lecture. Questions, please.
Yes, thank you, sir, for this great talk. Just out of curiosity, I want to know, is there any hierarchy between the regions, or like you showed that there is a coupling for tipping elements, right? So is there any hierarchy in the regions, like can we rank how this tipping element will move regionally?
Oh, that's interesting. I think what we ought to do is probably try to work out which ones cause the most harm to people, and then we could rank them on the basis of those impacts. That would be an interesting ranking to do. No one's really done that. In terms of regional things, well, yeah, you identify that sometimes the tipping point means a change in the regional pattern of climate that could have more, and that could be larger in some cases than others. So it can have more effect in terms of moving people or moving where agriculture is viable for some tipping points than others. So yeah, you could imagine ranking on that basis. And that would suggest that the monsoon tipping points, if they exist, are obviously a huge issue, but also because they're coupled, you'd conclude that the ocean circulation tipping points would also be really important because they change the whole pattern of climate. Yes. Yeah, so I think they're the ones I may worry about the most, particularly as they could unfold quite fast.
And one more thing. Can you please show me the slide in which you mentioned the proxy? Like, I guess it is a second slide.
Oh, the proxy of the
Holocene period,
yeah. Let's share screen again. I'll find it for you.
I just wanted to know that before the Holocene period, there were high fluctuations, and then the fluctuations were very low later.
Oh yeah. So we can probably see that if we look at.
I guess
hold
it was
on a second. Oh, I'm still on the slideshow. Sorry, I'll have to go backwards. We'll go backwards a bit. So do you want to go right back? Do you want that one, or do you want to go right back? We can go right
back. Not go this right. One, yes.
Hold on a second. But yeah, the one where you can kind of see by eye. 1 second. Yeah, so you see that the Ice Age is a much less stable climate than the Holocene as seen in Greenland. But you also see at the bottom, whoa, the fluctuations suddenly slow down here.
So I just want to know, is there any particular reason that before this Holocene period, the fluctuations are high, and after the onset, they have they've been suppressed, I guess?
Yeah, so that's a great question. Remember, in this case, we're looking in Greenland, so we're looking in the highish northern latitudes. In the Ice Age, what we're seeing, I guess, is that there's greater internal climate variability at those high to mid latitudes. Now, that can be the case because you put some great big white ice sheets on the northern hemisphere and you've created a stronger temperature gradient between the tropics and the pole in the northern hemisphere. And that's going to tend to drive faster winds around the mid latitudes and the higher latitudes. And that, in simple terms, is one of the reasons why you not only got faster winds, but you've got a more volatile climate, if you like, in the mid to high northern latitudes when you've got an ice age. There's no doubt more to it than that, but that's a beginning of an explanation for why, even without these abrupt warming events, the baseline variability here is more than here.
Yes.
But that's not necessarily true if I was looking in the tropics. So unfortunately, I haven't got a slide for India or China or whatever, or say somewhere more tropical. But in some monsoon regions, it's sort of volatile in the Holocene as much as it's volatile in the Ice Age for the water cycle.
Okay. Thank you.
Great, no problem.
So anyone is having any more question?
Hello team.
Hi.
I just wanted to ask you, in one of the slides you showed that there is this early warning indicators are more evident in some higher latitudes than in the middle.
Yeah. Shall I try and find that one again?
Yeah. So is that like the indicators? So probably I missed that part. So is it certain tipping element you were talking about, or is it like the?
It was a specific one, yeah. So this was, sorry, it was for the Atlantic overturning circulation.
Right. So then why do you think there is this like why is it only in
Good
those
question. Yeah, so to explain that, we're looking, so just to say again, this is where's the best early warning for the Atlantic meridional overturning circulation. And the reason there isn't a good warning between 40 degrees north and 20 degrees south is probably got something to do with the fact that there's a lot of wind-driven overturning and mixing of the ocean, particularly, where the trade winds blow through in the northern hemisphere and in the tropics as well. I think that is partly interfering with the signal, because ocean circulations are pretty complex things with multiple things driving changes in circulation. And I think what we see at the northern boundary is the thing we're really interested in, the thermohaline circulation, if you like, playing more of a dominant role in controlling the circulation changes, and that being more detectable up here. As for the southern boundary, it comes into lower latitude, so it's quite interesting, but maybe it has something to do with the fact that this is where the Atlantic connects to the rest of the global ocean, and we know that you can get a physical process-based signal of stability of the Atlantic there, and it's to do with whether the Atlantic is importing salt from the rest of the global ocean or exporting it. And that, again, it may be something to do with the fact that this crucial salt and heat transport exchange is maybe a more important part of the circulation right there, and it gets masked in here by lots of other things, particularly wind-driven circulation. That's my guess. It's a sort of guess in the sense that I haven't got a formal proof of that, but yeah, thanks.
Okay, and then so yeah, just to follow up, like so out of curiosity, I'm not very aware of the system, but yeah, I'm thinking that if so then, as I understand this is like due to some kind of special heterogeneity, right? I mean,
yeah, exactly.
So then, do you think that if this kind of heterogeneity can actually lead to like is it possible that the whole instead of the whole system collapsing, a part of the system may collapse? Or
that's a very good question. That's certainly the possibility for, say, the Amazon, which I talked about. So this I've started to think about the kind of categorization of these systems. So in the case of the Atlantic overturning, the crucial feedback that could give rise to tipping operates at the very large spatial scale. It's to do with the advection of salty water being by the circulation itself, supporting the sinking. So the big question to ask is, what scale is the crucial reinforcing feedback operating on? So with the Atlantic, it's at the whole scale of the Atlantic, and therefore the tipping can occur at the whole Atlantic scale. When it comes to the Amazon, it's maybe less clear. There is a recycling of rainfall that goes on over hundreds, if not 1,000 kilometer scales. So you could get the possibility of tipping coming out to large scales, although it probably would happen through a kind of cascade. You'd have a medium scale tipping, and then that would shut down the rainfall recycling, and it would cause further tipping. There's also in the Amazon this localized feedback where the wet forest suppresses the fires that helps maintain the forest. But if the fires get started, they dry things out and they cause more fires. But that spreads from a very local scale. So the Amazon is probably a good example where we're still trying to work out the scale, the heterogeneity of tipping, basically. So yeah, there's not really here in the slides, but in the most recent models, you can find like localized tipping points in the Amazon up against the Andes in the south. And in some of the models, it depends what the model represents, but in some models, the tipping can then propagate to other spatial regions, but it is heterogeneous. So great question. Yeah, it's a bit like phase transitions in physics, if you like. That makes, if you're all familiar with that concept, you know, when before a phase transition, you get clustered phase transition before you know, the whole supercooled water freezes or whatever. So you can think of it a little bit conceptually for some of these systems like that, I think.
Okay, thank you, and thank you for the very nice talk.
No problem. I might stop sharing the screens.
Yeah. So let us thank again, team, because we are running out of time. And so thank you, team, for this excellent lecture. Thank you very much.
Yeah, great to be with you. I've enjoyed watching some nice pictures of your campus. I'm feeling jealous I couldn't make it over. So nice to see you.
Hope next time you will be able to make it. Thank you.
Yeah, I hope so.
Thank you.